Hi, welcome to another video. This one's a tutorial on simple wireless chargers, or inductive chargers, some people might call them. So what you see here is, I think it's a 3-watt LED. It's running about 7 or 8 milliamps at the moment because I've got the power turned down, and one inductive wireless charging coil. So that coil was from Element 14. It costs £4.51 plus the VAT. So I thought I'll give you a quick demo. So that's the coil. That's not a smoothing capacitor, that's a 15 nanofarad tuning capacitor. As I say, a 3-watt LED, no rectifiers. You can rectify it, smooth it, and put FETs on it and modulate the output. But so if I just show you, just slam it on. It's not, let me turn the light off so you can see it. Hold this bit of paper because it gets better. So you can see it's not too sensitive. You can get quite a decent amount of current no matter where you move it. So considering they're small coils. So this tuning capacitor, what the idea is, with the frequency running into the transmitter and the receiver, you want the coils to resonate. So this coil is 45 millimeters by 30. So tiny little coil, fit inside a mobile phone. But for this resonation business, you want to tune the coil to the capacitor, or the capacitor to the coil, and that varies depending on what current and what voltage and what load. So when I say like you want it to resonate, it's a bit like, so this really, if I stick this on the table here and bounce it, so that's resonating slowly, and the idea of this capacitor, you want that to be in tune with the coil itself. Well, you can see with this current setup, I've got the transmitter running at 5 volts. You can turn it up a lot more, so you've got a fair bit of play in this. I think that's when they're perfectly aligned there. So you can always mark, if you're going to use it, you can always mark the base where you set the transmitter. So it's not all doom and gloom, and it's not like unsensitive. So let me remove this bit of paper. And underneath, that's, nearly broke it. Underneath, that's 5mm thick perspex sitting on this coil. So if I just show you again, so it's 5mm, and obviously a mobile phone case, I've taken mine off my Sony Ericsson. So 5mm perspex, if I sit that in the phone case as well, and we've still got power. So if I leave that there for a minute, let me show you the power supply. So that's running at 5 volts, drawing 10 milliamps. Although the voltage is turned down, from measurements I did earlier, this LED is drawing about 5 or 6 milliamps there. And I can turn the power supply up if I want to up 10. So now it's drawing 20 milliamps. And the LED is a bit brighter. Obviously it becomes less sensitive to where you're going to put it depending on what the voltage was, but I thought I'll show you. You can run it at 5 volts, 10 volts, and depending on what load you've got, with this FET I'm using, you can run up to 30 volts, but you then need a heatsink. So I might demonstrate if I've got time later. I cobbled together, because of this pack on this FET I'm using, didn't have a heatsink, so I just got 2 plates and clamped them to it earlier when I was doing some experiments. It's actually taken me a while to get the timing right. So 5mm perspex and a phone case, and we still get a decent amount of power. And let me turn it back down to 5 volts. So that's 5 volts. So what I've got, this 5 volt supply coming in here. It runs straight to the coil on one end. These particular coils from Farnell, as I say, less than fibre, they've actually got 2 windings in there. Makes them terribly efficient. I think it's got some sticky plastic on the back, so I could peel it off and stick it somewhere, stick it in a mobile phone or whatever I want to run. So the power runs through this coil. Then at the moment, for the experimental purposes, I've got my scope triggering the gate on this FET, which is his left pin. So it's a gate, source and drain. So what happens, the power comes into the coil, through the FET and down to ground. This is a high speed diode, although this is something like cable running 80 amps or something like that. This was actually, when I was doing trials earlier with some heavier currents, this was getting red hot, so depending on what you're doing, if it's more than say 10 or 20 milliamps load, you need a heatsink on this and a heatsink on this diode. If you're only going to run small currents or small loads, you get away with a smaller diode. This is 100k across the gate to ground, stop the gate floating, and that's it. So one diode. This is a 30 volt FET, 5 volt gate current, I think we can go up to 10, 30 volts max between the drain and source, and just a fast diode, and then a coil. So that's it. There's obviously no feedback with this circuit. If the voltage is going to get too high on this, there's nothing to modulate it into. Yeah, so it's actually better to put something in the middle, because that's what they're intended for. So that's the transmitter side. That's obviously the receiver. One coil, identical coil to that, just bought 2 of them. One tuning capacitor, got it on a drawing I'll show you later, and this is a 3 or 4 volt 3 watt LED. Right, so I've been messing about with the scope. Compliments of Element 14. I've got this software on there. So if I show you how I started it, so we're on pulse at the moment. I'll change it to my square wave. That's what I used initially. Right, so I'd recommend a scope if you got the money. If you're looking for a scope, certainly get this Agilent digital storage oscilloscope X2012A, 100 megs. But this one I upgraded, got the waveform generator, and you get square wave, sine waves, stuff like that. But it doesn't stop there. It's got radio frequencies, FM, AM modulation, that sort of stuff. But so I thought I'll experiment with this scope and see what I can get out of one of these coils without using a FET driver. Right, I'll try and not confuse the issue. If I said 100 kilohertz earlier, I was wrong. These coils are, I've just double checked, 125 kilohertz is the center frequency, but depending on what you're running, like for example I tried to run this string of LEDs, they wouldn't run at 125, 130 kilohertz. And also once this scope gets up over 100 kilohertz, it jumps up in tens. You see like down the bottom there, 130 kilohertz. If I try and adjust that, it goes 140, 150, and because it's going off frequency, the LED's going dim. So as we come back on to the center frequency, it's actually brighter there than 130, so slightly under the center frequency. The LED is nice and bright. Where are we? Down there. But you've got to look at the power supply as well. Look at what current the power supply is drawing. So it's a sort of compromise. Do you want it drawing minimal amount of current, or drawing more current and be more versatile to run more stuff, but then everything starts getting hot. So if back on the scope, I think I had it running at 87 on, or square wave PWM is running at 87 kilohertz. So this is like 20% duty cycle, and I can't turn the duty cycle down any more than that. So you see over there in the corner, period 11 microseconds, duty 20%. So what I did, because I know you guys won't necessarily have a sort of, well, actually £1,500 scope with the software. You won't have a £1,500 scope to mess about with the software and look at the results you're getting on an LED. I decided to program a PIC microcontroller for you, and I'll show you the program. And I set it at the 87 kilohertz instead of 125. So let me show you. If I change this to pulse, the current drops down from 40 to 20 milliamps. So if I go back to square, right, we're up at 40 milliamps, running 20% duty cycle at 87 kilohertz. But change that to a pulse, we're down to 20 milliamps. So I decided to set the microcontroller to this slower frequency. See now it's drawing the least amount of current. Let me turn that voltage down a bit, it's creeping up. So 10 volts, 20 milliamps at 87 kilohertz, 5 volts peak to peak. The width is 2 microseconds of the pulse, and the period is 11 microseconds. So that's what we're running the transmitter with. And you'll see it's still going, so at 87 kilohertz. It's running nicely. So now that bit of paper's out of the way. So depending on what coils you've got, what load, what voltage, you really need to mess about with these capacitors, and obviously the frequency. So let me, I'll show you the code first, the code and the wiring diagram. Well, this is how I wanted to wire it up. FET driver, PWM in, 2 FETs, and the load in the middle, the coil in the middle. Farnell didn't have any in this country, they're all in Liège, Belgium or whatever. So I had to abandon that, and I had to wait till Tuesday for them to come, and I thought, no, I want to mess about with the coils now. So I'm surprised with the results I got. I was quite pleased. So that's the proper way to drive this coil, and this is the way I did drive it. So I've got the microcontroller set up ready to show you that it works, but I've got the scope here, and I was varying the duty cycle and pulses and all that sort of stuff with the FET to see, yeah, the results. So obviously there's one coil. So the FET I'm using is that one there. Have a look on the internet. So it's a 30 volt FET, 160 amp peak. I've got the high speed diode there, 100k resistor across the gate to ground, and that's my 33% duty cycle coming in. And I've pre-programmed this 807. It's actually on a clock PCB, but I'll show you in a minute. Right, so that's how we're running it. That's simply a couple of components in your way. So if you want, you can mess about, put a tuning capacitor across the transmitter. I did actually mess about and got a few extra millivolts, but so look, no wires. Right, and this is the receiver. So that's the receiver coil, identical to that one. 15 nanofarad in this example I'm using here, but depending on what you're running, if you run a heavier load, you need to start upping this capacitance and then your load. So that's the wiring diagram. I've got some little notes down here. So the cause and demo from final element 14, that's the part number, costs £4.51 plus VAT each. If a high Q, that's wrong, that should be 125 kilohertz. There are some at 100 kilohertz, but these are 125, so that's wrong, 125. So that's it for the wiring. Can't get any easier than that, can you? And what I've programmed the microcontroller. Drop this down out of the way. This is, look, I can't scroll up and down the page because that's it. So unsigned short. This was part of a program. You don't have to put all this. You can put it down there, but this is part of another program. I just copied it and altered it to what I want. So unsigned short. So current duty, old duty, current duty 1, old duty 1. But that's because Microelectronica's demonstration program had some buttons so you could alter the duty cycle and alter the frequency, but obviously with this example we want it at one frequency, so I tried to set it 87, 88 kilohertz and 88 kilohertz went to 91 on the scope, so I put this at 86 kilohertz and that seemed to give me about 87. Don't know if that's the discrepancy in the timing and the resonator I've got. So duty cycle 33%, PWM start, PWM1 set duty, current duty, which is at there, 33%, and the frequency PW1 up there. So this is a regular 887, just a spare clock PCB. That's the output I'm going to put to the wireless charger coil transmitter. There's an 8 meg resonator down there. That's all, nothing else. So you could get away with a small 14-16 pin chip. I just happen to have one of these ready. So let me connect this up. Right, this is that PIC microcontroller, PIC 887, 8 meg resonator, as I said. That's the scope connected to the output. So let me just show you on the scope. So we've got some overshoot, and I know that's not the scope, that'll be the microcontroller. So you can see frequency 87.1 kilohertz. That pulse width 1.3 microseconds and the period 11 microseconds. So same as that PWM on the scope, which I've now turned off. Hopefully you're happy with that. So I'll now connect that up to the transmitter, or the wireless charger transmitter coil. In fact, I will show you. So this has been powered up off the in-circuit serial programming port. This white wire is my signal. Don't have to worry about the ground because it's connected to the ground on a PC, which has got a common earth with my power supply. So I had a 100 ohm resistor here, just didn't want to blow up my scope. So I'm just going to go straight to the gate. And there we are, nice and bright. And that's running off the PIC microcontroller at 5 volts. So if I had 5 volts or 4.9, milliamps. So I can wind it up. So it's now going to start drawing more current, obviously. So it's 150 milliamps, and look at that LED, blinding. So let me just connect. I'll turn that voltage down a bit. So now this FET is going to be getting hot. I know it is. Well, it's not too bad at the moment. I'll leave it like that for a minute. So I forgot to show you, when I had this running on the scope, 125 or 120 kilohertz, this was drawing 10 milliamps with no load. So if I take the LED off, now it's running on a PIC micro because there's certain tolerances, that sort of stuff, and the frequencies and capacitances need changing for a lower frequency. But this was drawing 10 milliamps as you saw. Now it's running on a PIC micro. It's running 20 to 30 milliamps. But the specification for this coil, when run at 125 kilohertz, it will draw 10 milliamps, and you saw on the power supply earlier that's what it was drawing. So that's drawing between 20 and 30, so probably like 29 the way that 3 is coming up. If I stick the LED on, it doesn't actually draw anymore. So let's see if I can get you both in view. Hopefully you can see that green number on the power supply. So on 20, well, it seems to have stopped going up now. That's odd, isn't it? So if I take this off, it started going up. That's probably because that transmitter coil wants tuning. But you can mess about all day with tuning capacitors, but I thought I'd just give you the basics. And I could be here all night telling you what to do. And rectifiers and modulators for this receiver, and you could have this running a device and then look at my other videos, have a Bluetooth transmitter and receiver, have it sending information back to the transmitter. There are some custom chips for these wireless devices, a charge controller, and the transmitter will talk to the receiver and the receiver will talk to the transmitter. So, and that's how the proper decent one, a decent equipment like medical equipment, that's how they control the charging current or charging voltage. They do talk via these coils. So what I'll do, I'll put the scope on this and you can see it, and then I'll stick these LEDs on. So let me, one on there. So obviously we're using a diode as a rectification. The thing is, because this is so light, the scope wants to pull it all out of the way. Right, this is what I was doing earlier, messing about with the frequencies and pulse width, that sort of stuff. So if I go back to the scope, so I'll move the LED on the perspex. Remember, this is sitting on 5mm perspex. Your phone's going to be a lot thinner. Right, you can see we got 7.5 volts peak to peak, and if I press the coil down onto the perspex and move it around, there's 8.4, 8.5, 8.6. But you can see where this is moving and that pattern's changing. That's how I understand, that's how the proper receivers communicate with drivers. So if I turn this all the way around, still at 8.4. So 8.4 volts peak to peak, and that power supply is running at 5. So it's, considering it's just one FET, one microcontroller, no sophisticated management, I think we're doing pretty well for a wireless device. I'll show you. So look, you can see how, hopefully you can see how far I'm lifting it up. Hopefully you can still see the LED. I'll get it in the right place first. So look, that's half an inch there, or 10 mil maybe. And the LED's still on there, hopefully you can see that. So pretty good. Right, let me connect up this longer string. So look, I've just dropped that back down anywhere. We've still got 8 volts peak to peak, 5 volts going in. If we turn the power supply up, the FETs are going to start getting hot. So now we're at 150 milliamps. That's probably drawing too much current. And we got 12.9 volts. Right, let's connect up a higher voltage load. Right, I've connected this string of LEDs. These are 12 volt, and I know they draw over 100 milliamps, about 110, 120. So obviously we're going to overdrive these now, so it's going to be drawing more than 120 milliamps. But I can't be bothered to put the meter in. So same setup as before. So at the moment, if I turn the light off, I don't know if you can see, they are actually glowing very slightly. And you can see we're still running off the PIC microcontroller, so current's up at 40 milliamps. Oh look, as you can see, so with this heavier load, the current does actually go up from this power supply. Oh, actually, look, just moving it about, they've got brighter. But obviously, because of we want more voltage, that it's got to be spot on in the right place. It's not quite spot on, but we've got some results there. They're glowing, and the current's gone up from 20 to 40 milliamps at 5 volts. So you see on the scope, we're getting some measuring across that coil there. So we're measuring this voltage on this receiver. Get the LEDs back on, moved it. This is now getting hot because of the higher current and this diode. This diode is quite warm already, and we're only at 40 milliamps. But 40 milliamps on that coil, we've got 18.7 peak to peak. So obviously that diode's working, cutting out any spikes. So you can see the waveform's changed from that lighter load. So what I'll do, I'll turn up the voltage. That's back up to 10 volts. We're at 150 milliamps, and those LEDs are nice and bright. So let's go up to 15 volts. As I said earlier, it's all a compromise here. What load do you want to run? What voltage and current can you afford? So obviously you start losing efficiency with this circuit. You know, it's just cobbled together. You know, one FET and one PIC microcontroller, or any microcontroller sending out one square wave. How easy can it get? So 15 volts, 210 milliamps. So I know these are drawing just over 120. So we're probably down to 50% efficiency. But obviously with the higher voltage, apart from the brighter, it's still fairly sensitive. It's more sensitive with this higher voltage. Or to try and get the higher voltage. Turn it around. Seem to be less sensitive when it's this way. Obviously the magnetic field is cutting through the coils there, but it's definitely better with this high voltage when it's lined up properly. So 15 volts there, and 27 peak to peak. What's that trigger? Can't get it to a trigger to measure the frequency, so no. Right, let's turn the voltage up even more. So that FET's rated at 30, so let's turn up 25. So 25 volts going in, and look, the voltage hasn't gone up much more. Current's gone up to 260 milliamps. And you can't see it because these LEDs are so bright. So that's what you're up against. I was quite pleased. As I say, I wanted that FET driver, but it was out of stock. I'll turn that voltage, like that voltage, back down to 10 volts on there, and a string of 12 volt LED lights are going happily. Obviously it's more sensitive, as I said, than the small load. Depends what you want to do though. Don't forget this is sitting on perspex, that's 5mm thick. So if you wanted to know how wireless charging works, now you know. This is obviously a basic example, no power management on the receiver side or the transmitter side. Incidentally, this is the basic principle of medical devices as well, that plant something like this receiver inside the body under the skin. My brother in Australia has actually got an implant in his back, had some trouble with his neck. They planted a spinal stimulator which powers some electrodes and stimulates the nerves to cut out pain. So he's got one of these similar devices, obviously with a microchip, implanted in his back, and that's under the skin, and you'll come along with a soft transmitter, stick it on the outside of the skin, that charges the internal battery, and obviously being medical, there's a different grade, and they'll communicate with one another. So it's not just mobile phones, it's medical stuff, or wherever you need to get through a barrier. And obviously the demonstration today has been through 5mm perspex, and the human skin's a lot thinner than that. But so maybe it's given you some insight. Maybe you already knew. Now you know how to rig up a simple circuit to get your own going, and cheaply too. So yeah, that's it. I'm pleased, more than pleased with the results. Look, so one coil, one capacitor, and whatever load you want, one FET. Well, it's not too bad now. It's with the heatsink on, running 160 milliamps at 10 volts. This is actually only warm to touch. Yeah, this diode is red hot, too hot to keep my finger on it, so be careful about what diode you're going to choose if you're going to make your own circuit. To reiterate from before, these are sort of less than £5 from Element 14. The FETs are less than £1. So, job done. Bit of a long tutorial, or talk through, but obviously you can appreciate there's a lot to go through. So if you find this video helpful, or you like it, please click like. Thank you very much.